Thank you so much for introducing me. So, at first, good afternoon to everyone. So, thank you for giving me the opportunity to deliver a talk on the dispersion of solute in blood flow through microvessels. So, this study have lot of applications in the blood flow. Basically, the main application to this study is solute dispersion, drug dispersion in the blood flow. So the outline of my study of lecture is the introduction. At first, I will briefly introduce to the blood flow analysis. Also, I will give the motivations to the study, and then I will discuss some relevant mathematical models to the blood flow analysis in the dispersion process. Also, I will solve those models by applying the analytic method. To solve the velocity distributions, I will apply the perturbation technique. Also, to get the concentrations of solutions, I will use the eigenfunction expansion method. Also, I will describe the significant results to the blood flow analysis in the dispersion process, and hence followed by some major observations in our study. So the motivation of this study, the study of the solute dispersion process has always been an interesting topic to the researcher due to its output applications in different areas like biomedical engineering, physiological fluid dynamics, environmental dynamics, and chemical engineering. So most relevant applications, important application in the blood flow uh, are the dispersion of drugs. Not only that, also the transportation of proteins and nutrients. So, in our study, main application to the solid dispersion process is the dispersion of drug. So, what is the importance of the studying this dispersion of the drug? So, if you see this, mainly the drug have a significant effect to cure some diseases. Also, if we study the magnetic dark targeting, so with the nanoparticle assisted dark delivery process, that will help to cure the cancer-like diseases. In our study, the main aim to get the concentration of the solute in the blood flow by considering blood as several non-Newtonian fluids. Here, the main motivation to the study to get the concentration of the drug is that so drug can be therapeutic and toxic at different concentrations. So if the concentration is high, drug can be toxic and it will be harmful to our body. But if the concentration of the drug is low, so that can be effective and we can cure the diseases. So that's why it is so important to study the concentration of the drug to treat the several diseases. So before starting on the solid dispersion process, I want to briefly discuss on the microvascular region. So what is the microvascular region? So microvascular region is made of the vascular region and extravascular region. So microvascular region is made of by the blood vessel and blood. And what will be seen for extravascular region? So for extravascular region, we can see the living cells and the interstitial fluid. So that means we can say that outside of the vascular region, means outside of the blood vessel, we can see the extravascular region, and that there we can see the tissue region. And but in our study, we are only focused on the vascular region, so which is consisting with the blood vessel and blood. And blood has several components. So the main components are the cell elements and the plasma. And cell elements are the RBC, red blood cells, and white blood cells and platelets. And the several blood vessels are the arteries, vein, and capillaries. And arteries can be small arteries, like it is called as arterioles, and can be its larger artery, that is called as aorta. So similarly, it can be seen for vein also. So in our study, we are only focused on the uh, solid dispersion process in the blood flow through the small arteries. So this is the symmetric view of the microvascular region, and we can see that the blood vessel, and outside the blood vessel there is tissue region. So now the flow properties of the blood. So this is the symmetric view of the blood flow. When the blood flow occurs, we can see the RBC move through the central axis of the tube, and it is concentrated more to the central axis of the tube. So we can see that the RBC region is near to the central region of the tube, but WBC and platelets and other component of the blood, that is plasma, it can be seen near to the wall region. So we can say that the blood rheology is strongly affected by the RBC. Why? Because we can see that RBC have the uh, large volume fractions in comparison to the WBC and platelets. So that's why in the blood flow, WBC and platelets don't have any effect. So we are only considering the RBC, the effect of the RBC. And here also, due to the rhythmic pumping of the by the heart, we can see the blood behave like pulsatile in nature, and also we can see the sinusoidal flow during the blood flow. Also, blood can behave like Newtonian as well as non-Newtonian fluid. Let's see this. So before going to discuss that about the blood flow as a behave as non-Newtonian fluid, I will briefly discuss about the non-Newtonian fluid and Newtonian fluid. So what is Newtonian fluid? Newtonian fluid which follows the Newtonian law of viscosity. And here we can see that shear stress and shear strain relationship is linear, and mu is the viscosity which is constant here. So, but for the non-Newtonian fluid, we can see that shear strain and the shear stress relationship is non-linear, and we can get the viscosity is not constant. Here it's depend on the shear rate, strain rate, and this type of viscosity is called as apparent viscosity. If you see this figure, we can see that the Newtonian fluid is given by this. It is maintaining the linear relationship between the shear stress and the shear strain rate. And whereas this calcium fluid, it is non-Newtonian fluid, we can see the non-Newtonian, we can see that non-linear relationship between shear stress and the shear strain. So now the questions come to this: why this blood behave as non-Newtonian and also sometimes Newtonian? So because blood viscosity, we can see that it's depend on hematocrit, which is mostly depend on the RBC, and the shear rate and the protein content in the plasma and vessel diameters, and several aspects are there. So when we see that for large vessel, we can see that blood behave as Newtonian, and for this this vessel, we can see that high shear rate can be seen, and due to this phenomena, we can see that blood viscosity is constant. So that time we can see the Newtonian effect of the blood. But when we consider the small vessel, means very small vessel, there we can see that blood nature is strongly affected by the non-Newtonian fluid. And there we can see that low shear rate, and due to this low shear rate, we can see that RBC have more effect, we can see, and due to the aggregation and deformation and the alignment of the RBC, we can see the non-Newtonian nature of the blood. Also, not only non-Newtonian nature can be seen for small vessel, sometimes also disease condition, we can see non-Newtonian nature of the blood for high radius of the vessel also. Means that time, what we can see, that time the RBC can form the rod shape structure, and it can aggregate and form the one microstructure, and that will give the non-Newtonian effect. So means, but for without of disease condition, we can see for normal conditions, small vessel, we can see that non-Newtonian effect. So what will be the suitable non-Newtonian fluid to the blood flow? So there are several non-Newtonian fluid. which is relevant to the blood flow in small vessels. So these are all experimentally validated fluids. And now, at first, I want to discuss the constitutive equation for Casson fluid. So here we can see that shear stress and shear strain relationship is non-Newtonian here and non-linear here. Here we can see that this model is the two parameters model and containing the shear stress, containing the yield stress and the apparent viscosity of the fluid. So here we can see that when the shear stress exceeded the yield stress of the fluid, then flow occurs. Otherwise, it will not flow. So also we can see for this kind of fluid model, we can have the two regions. One is the plug flow regions near to the tube wall, near to the center region of the tube, and outside the plug flow regions, we can have another region. So and we can see that in the plug flow region, the velocity of the fluid is constant. So we can have the bland shape profile. So, but outside of the plug flow region, we can have the parabolic shape profile. We'll see this later. So, and now there is another fluid models, non-Newtonian fluid models. This is also very important for small blood vessels, nearly less than 65 micrometer in radius. We can have the more significant effect of this Herschel-Bagley fluid. So here, this is this model shows the three parameters, and these parameters are the apparent viscosity and the yield stress of the fluid and the power law index. Here we can see that similarly we can have the two regions. One is plug flow region and outside plug flow regions. And also these models describe the shear thinning and thickening behavior of the fluids. And also we can get several fluids from this fluid model. Like Newtonian fluid we can get the power law fluid, we can get the Bingham fluid for considering different parameters. Now there is another relevant blood flow models, that is non-Newtonian fluid models, that is Coriolis fluid models, and this is relevant to the small arteries. Not only that, also it will be validated to the medium-sized arteries also. So these fluids models consider the five parameters. Here parameters are the zero shear rate viscosity, infinite shear rate viscosity, time constant, and Joshua parameter, and the power law index. And we can see the significant effect for this fluid model during the dispersion process. So now I want to discuss two relevant single phase and two relevant blood flow models, that is the single phase and two phase model. And what is these models? I will discuss them. So at first I start the single phase blood flow models. So this is the symmetric diagram of the proposed model, and here we are considering the blood as non-Newtonian Casson fluid, and also we are considering the straight circular cylindrical tube as a blood vessels, and here we assume the small and medium-sized blood vessels. Also, we assume the wall absorption present at the tube wall, and a one-dimensional flow in the axial direction is considered here. Also, also the dilute solution is considered. So now, since here the blood is considered as non-Newtonian fluid Casson fluid models, so we have the constitutive equation given by this. And since this blood only treated as the Newtonian fluid, that's why it's as known as single phase blood flow models. So this already you know the constitutive equation for Casson fluid. So now the momentum equation for Casson fluid is given by this with boundary conditions. Shear stress is finite at the center line of the tube, and the no slip velocity at the tube wall. Also, we have considered the blood flow is pulsatile in nature. So that's why we have considered the pressure gradient in this form. So here P0 is the steady component of the pressure gradient and P1 is the unsteady component of the pressure gradient. and omega is the frequency of pressure pulsation. But our main aim to find out the concentration of the solute. That's why we have introduced the governing equation for solute concentration by the unsteady convection diffusion equation by this. Here the right hand side terms due to the diffusion, and dm is the molecular diffusivity coefficient. And here the left hand side terms due to the convection. And here this PD is the parabolic PD. So now we have considered the initial condition and the boundary conditions. After the injection of the solute is distributed through the cross section of the tube. Here the solute mass is m. So we have introduced the initial distribution like that, and boundary condition are given by this. Due to the symmetry at the central line of the tube, we have the solute flux. This vanishes here. So we have this, and also we have considered the wall absorption at the tube wall. That's why we can get this condition. Here the left hand side, this is the due to the solute flux, and this is the right hand side, this is the concentration at the tube wall, and K is the reaction constant here. And also we have considered the finite amount of solute in the system. That's why at infinite distances the solute vanishes. So we have that conditions. So here we have used the non-dimensional variables to get the non-dimensional form of the equations. At first we obtain the governing equation in the non-dimensional form in this way. So now the constitutive equations for Casson fluid in the non-dimensional form is given by this, and the momentum equation in the non-dimensional form is given by this. And here we are interested to find the velocity of the fluid by solving this momentum equation 23. So here we have used the perturbation technique to find out the velocity of the fluid. And here we can have that epsilon is treated as the perturbation parameter, because the epsilon is very, very small here. And it is the 1 by Schmidt number, and Schmidt number for arterial flow is seen to have more, likely it's 10 to the power 3 for arterial blood flow. So that means epsilon is treated as very small quantity. So we can consider as part of parameter here. So the velocity distribution for Casson fluid, it is for the single phase fluid velocity, and we can get these solutions. And W1, this is the velocity for plateau regions, and W2 is the solutions for velocity distribution outside the plateau region. So now we obtain the velocity profile for one phase, single phase fluid model. Now I want to introduce the two phase fluid models. So this two phase fluid model is very important for very small arteries, and we'll discuss this. And here we can see the symmetric diagram of the proposed model. Here the central region of the tube, we can have the core region of the red cell, and we can see the near to the wall region, that is called as a peripheral region. So we can have the presence of plasma there. So this we can see here from this figure, the RBC is centered to the central line of the tube. We can see the more presence of the RBC. That's why we can see the non-Newtonian nature of the blood near to the central region of the tube. So that's why the blood is treated non-Newtonian fluid near to the central region of the tube. That is the core region of red cells. And outside that, due to the presence of the plasma, blood is treated as Newtonian fluid here. So we have here considered blood as two fluids. One is the Newtonian fluid, another is the non-Newtonian fluid. That's why this type of model is considered as two-phase blood model. So now I want to find out the fluid velocity of these models, and others consideration are the same here. So here we can see for small blood vessel, we can see that apparent viscosity can be affected by the Fourier's Lindvik effect, and this can be obtained by this. And this is experimentally validated result, and we can see that mu1, this is known to be the non-Newtonian fluid viscosity, and mu2 is the blood plasma viscosity, it is known as the Newtonian viscosity. So now we have introduced the non-dimensional variable to get the non-dimensional form of the momentum equation. And here we can get the two regions. So core region one, another is peripheral region. So we have the two momentum equations, and after solving that, we can get the velocity distribution for two-phase fluid. That is one we can get near to the in the core region. We can have the outside of the plug region, that is obtained by this, and another is plug region. So that is obtained by this. So these are the all fluid velocity of the non-Newtonian fluid, that is Casson fluid considered here. And this is the fluid velocity near to the peripheral region, and this is the Newtonian velocity we are getting here. So now we obtain the velocity of the fluid. Now we are interested to find the mean concentration of the solute by applying the velocity of the fluid to the governing equations. Then we can consider the solute concentration represented by this form, and after applying that in the governing equation, we can get the generalized dispersion model in this form. And here we can get the three transport coefficient, that is K0, K1, and K2. These are unknown to us, and this K0 is due to the, this is the exchange coefficient, this is the due to the non-zero solute flux to the tube wall. And this K1 is the convection coefficient, this is due to the fluid velocity, and K2 is the dispersion coefficient, this is due to the fluid velocity as well as the molecular diffusion of the solute. So these three transport coefficients we need to find out. So how we can find out? So if you use this model to the governing equations, again we can get the differential equation in terms of the Fn and Kn. So from this, so we can have the three equations, differential equation we can get. So from this, we can easily obtain the K0, K1, and K2. So here we can see the first eigenvalue problem for F0 and K0. So after solving that by eigenfunction expansion method, we can get that we can get the eigenfunction F0 is obtained by this, and the eigenvalues K0 are obtained by this. So now we use this F0 and K0 to obtain the F1 and Q1 from this eigenvalue problem. And here also similarly, I have used the eigenfunction expansion method to get the F1 and Q1. So now again we are getting F1 K1, and we use this F1 K1 to find out the F2 K2 from this eigenvalue problems. And again we are obtaining the solutions for F2 as well as K2 by applying the method of eigenfunction expansion. So this is the K2 we can easily obtain after using the F1 and K1. So now already we have obtained the K0, K1, and K2. So we can easily use this to find out the concentration of the solute from these equations. So here the concentration of the solute is given by obtained by this. So now we have reached finally we have reached to the mean concentration of the solute. So now we are interested to see the results. So here we have considered relevant data to the small arteries. Here we are considering the radius of the artery from 30 micrometer to 100 micrometers, and we can see that for these micrometer tubes vessels, we can have the significant effect of the two-phase model. But exceeding that, we can't get the two-phase model. There will be significant of the single-phase model. We will see this, and also we can have the Oemersley frequency parameters in different arteries, and this Oemersley frequency parameter increases when the arteries size increases. So now this is the result for dispersion coefficient. This is the result for solid dispersion for Newtonian fluid considering the steady flow, and this validates our result, and we can see that our result match with the previously obtained result by the Gill and Shankar subramanian. And here we can see that initially solute is transported by the convection of the fluid, and but when the time increases, we can see that the solute transportation not only depend on the fluid velocity, but also it's depend on the molecular diffusion of the solute. That's why we can see the solute dispersion becomes more effective in the systems, and also at very large time, it stabilize the systems. So now this is the dispersion. This is the solute dispersion for different arteries with single and two-phase models. So here we can see that for two-phase model, the solute dispersion is more compared to the single-phase models. And here we can see that for small size arteries, so there is significant effect of, but if you consider large arteries, we can see there is no significant effect for these two-phase and single-phase. So what do you mean by this? So means we can see that for small arteries, the single two-phase model is more effective. But for higher radius of the arteries, this is not effective. Two-phase model, two-phase fluid is acting like single-phase fluid. So that's why if you consider the high radius of the arteries, we'll go for single-phase. But when we talk about the two-phase model, so when we talk about the small arteries, we'll consider the two-phase model. And here also we can see as the radius of the tube increases, we can have the small dispersion. So why we are getting this? Because when the see the more absorption at the tube, and when we can see that for large arteries, we can see that solute dispersion become very small. And this is the solute dispersion for different rate of absorption. And this is the for single phase fluid models. And we can see that for higher rate of absorption, more amount of solute is absorbed to the tube wall. And due to this phenomena, we can see that solute is convected more higher velocity of the fluid near to the central region of the tube in comparison to the wall region. And we can see that near to the central region of the tube, we can see that the velocity gradient is more smaller, and due to this smaller velocity gradient, we can get the smaller dispersion. So means when the rate of the dispersion, rate of the absorption increases, we can have the smaller dispersion rate. And here also we can also see that the transfer diffusion also decrease the solute dispersion process. So also this is the for small arteries, and we are getting the single frequency period. But if you consider the large arteries, medium to large arteries, and we can get the double frequency period. And here, not only that, we can also see there is the negative dispersion occur. What is this? Why we are getting that? Because we can see that for medium to large arteries, the flow reversal period is same. And due to this phenomena, we can see that solute is moved back to the backward flow. And also, this type of phenomena can be seen in the experimental studies also. So, and that's why for the small and for the large and the medium size arteries, we are getting the double frequency period as well as the negative dispersion phenomenon. So now this is the variation of the mean concentration for different size of arteries, considering the two-phase and single-phase model. So we can see that for two-phase model, we can have the more concentration in comparison to the single phase. And why we are getting that? Because we can see that for two-phase model, two-phase fluid flow, we can have the more convection. Not only that, we are getting the more dispersion. So this will affect the on the solute concentration process. And also we can see for small arteries, that is for 30 micrometer of the tube, we can have the difference is more in comparison to the two-phase and single phase. We can see that. But this difference becomes very, very small if we are considering the large arteries. So means for greater than r greater than 100 micrometer of tube, so this difference becomes very, very small. That means it shows that two-phase model is acting like a single phase if you consider large arteries. So also we have considered the different fluid model to describe the mean concentration of the solute. Here we are considering the different fluid model, that is Hassel-Wagley fluid models, that is shear thinning fluid. And also we are considering blood as choriosity fluids and the choreo fluids and the Hassel-Wagley shear thickening fluid and the Poisson fluids. So we have considered blood as this kind of different non-Newtonian fluid, and we have compared our result for mean concentration. And we have seen that the choriosity fluid and Newtonian fluid behave like same. So there will be no effect can be seen on the concentration. On the dispersion process, we are also can't find any difference for choriosity and Newtonian fluid. But for Casson fluid, we can get the more concentration profile in comparison to the other fluids. So this is the comparison model for concentration of the solute by considering different relevant fluid models in the blood flow. So now I want to make some major observation here. So we have seen that the exchange coefficient, which is due to the non-zero solute flux at the tube wall, this is independent of the non-Newtonian nature of the fluid, and but it's depend on the only on the wall absorption parameter. And the other coefficient, other transport coefficient, that is convection coefficient and the dispersion coefficient, have the significant effect on the non-Newtonian nature of the fluid. And not only that, mean concentration also depend on the non-Newtonian characteristics of the fluid. And the convection coefficient, that is that depends on the velocity of the fluid, and also dispersion coefficient that depends not only the velocity of the fluid but also the molecular diffusion of the solute. So we have also seen that for small arteries, the negative dispersion can't seen. So only we have seen the positive dispersion there, and there we can't see any backward flow. And we got the single frequency period for small arteries. But if we consider the medium size to large size artery, then we can see the double frequency period. Not only that, we have seen the negative dispersion phenomena also seen, and this is due to the flow reversal period seen in the these large arteries, and the material also contracted due to this backward flow. And also we have seen the porosity of fluid is behave like a non-Newtonian fluid at low shear rate, but others non-Newtonian fluid have significant effect during the dispersion process. And also we have seen that for Casson fluid, the concentration profile is of maximum in comparison to the other fluids models. And also for we have seen that we have now I want to make the major important observation here, that is for small arteries, two-phase fluid model is more significant. But if you consider the higher radius of the arteries, if you consider more than 100 micrometers of the tube, that time single phase fluids have significant role, because that time this two-phase fluid model behave like single phase fluid model. And this type of relevance of this two-phase model also seen experimentally. So these are all publications. These are the references. Thank you. Also, can I say something? Actually, I have to tell about that because I have finished so early, so I have time. So I will. Yes, yes. So actually, here, when we are solving those kind of models, so we are having hello. Sorry for the disturbance. Actually, there was power cut. That's why. Mhm. Yes, 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 yes. Okay. So, is this visible? So, solving the this kind of momentum equations to get the velocity distributions, uh, we are using the perturbation method. But here we are lucky to get the this perturbation parameter epsilon. This is very very small. So what will be if there is the this there is no such kind of very small parameters. So that time this perturbation method will no longer will not be valid for this kind of case. So we have overcome this situation, and we have used the homotopy analysis method to find out the solution for those kind of problems. So, and also we have seen that the perturbation in the homotopy analysis results are more relevant. Also, uh, also it's better in terms of the perturbation solutions. So that's I want to say that. Uh, yes, 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 yes. Please. Yes, 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 yes. Very good question. So actually, we have seen that. So here, this epsilon is very very small. Why? Because it's depend on the speed number. So it is inverse of the speed number. We can see, and for arterial blood flow, we can see that speed number is order of 10 to the power 3. So arterial blood flow, the speed number is order of 10 to the power 3. That means we are getting above 10 to the power 3 values. So means we are getting epsilon is 10 to the power minus 3. So that means it maybe also more than that if you consider higher values of speed number, because also it exists. So then we can get the more small values of the epsilon. So means it's valid, we can easily apply the perturbation method. Hmm. 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 Yes, sometimes yes. Yes, yes, yes. We can get the solutions. Yes, yes. Sorry, please, please. Uh, because we can see, because if you want to correct the 4-5 decimal places result, so that time this first order solution is very very important. But if you want to correct only the 2 decimal places, then if you consider the only 0th order solution, maybe it will be the okay. But better to consider the first order, because this will be giving the more accurate values. Mhm. Yeah, yes, yes. Welcome. Thank you. Thank you. Thank you so much.